Imagine you're a human expert and you are responsible in your company for making sure the lights stay on in an entire neighborhood. Would you use a black box AI to help you with this? I don't think that I would. For such an important system, we need an AI that is interpretable, interactive, but also expressive. Of course, as a human expert, you would only use a system like this if you can trust it, right? Which means you must be able to understand it as much as possible. You also want to be able to interact with it. As a human expert, you probably have a lot of knowledge about the task at hand, and you want to exploit that knowledge. You want to make sure that what you know about the problem you can tell to the system. This way, the system does not have to learn from data what you already know. What you know, you should be able to tell. What you don't know, it should learn. And finally, it must be as accurate as possible, meaning it must be able to exploit all the data that we have. In our case, this means time series data and sensor data, but also image data. But the problem is that current AI systems are not able to do this. You have these traditional approaches like deep neural networks. They're very expressive, but they're not at all interpretable or interactive, as you probably know. And then you have these interpretability approaches. They're of course interpretable then, but they're not at all expressive, and they're also not that interactive in practice. So this is a problem. And this is the problem that we've been trying to solve. We wanted to come up with a method that does tick all these boxes. And I will try to convince you of that today, that we were successful in this, that our new method called Concept Memory Reasoner combines accuracy with interpretability in such a way that we can use it for nice applications like smart grid decision support. Note that we have not been able to apply it yet to this use case, but we want to do so as soon as possible. And to try to convince you that we will hopefully be successful in this, I will discuss the three main components of our model and how they relate to these desiderata of this use case. And to try to, well, I will begin with this with concepts. So concepts, they help us with giving nice explanations to human experts. Let's say we have some input image of a street, and we want to predict whether the houses in this street are linked by the same grid or not. Well, then in the first step, our model will extract concepts from this image. For example, it could be the case that it detects a cable spanning between two houses and a voltage pillar at one of these houses. These are then the concepts that it extracts, for example, using a neural network. In a second step, it will use these extracted concepts to make a prediction. In this case, predicting indeed that there is a link in the electricity grid between these two houses in the street. Now, typical AI methods don't have these concepts in the middle, right? Which means that if you're going to try to explain a prediction that such a typical approach makes, then the only thing that you can really do is refer back to your input image. You could, for example, try to explain which pixels in this image were important for predicting that thing over there, and which pixels didn't really matter in the end at all. But the nice thing is that if you do have concepts, then you're not limited to explanations like this. Then you can also give explanations in terms of the concepts. This is way more high level, this is way more abstract. This might be easier for many human experts to understand in practice. Instead of saying which low-level individual pixels were important, you can say which high-level concepts were important, or you can do both. That's your choice. The next component is logic rules, and they help us with our interpretability. You might already wonder, okay, but how do we exactly go from these concepts to this prediction? Well, I basically just spoiled it. We use logic rules. We use specifically what we call a rule generator. For a given input image, this generator can generate one or more logic rules. An example of a rule is, if there is a cable between two houses, then they are linked by the grid. Then that is our prediction. You have rules like this, you can apply them to your concepts, and this gives us the prediction. This is nicely interpretable because the rule very clearly and easily tells you how you go from your concepts to the end. And then the final component is really that rule generation itself that I just explained, because it is really this rule generation that is responsible for our interaction, but also for our expressivity. The interaction is quite simple. If you're a human expert and you have a lot of knowledge about your problem, then you can try to encode this in the form of logic rules. And once you have a set of rules, you can give this to this generator. This way, the generator knows these rules exist. It does not have to learn them from data. It can use them whenever it needs to in order to make a prediction. But very importantly, the model is in no way limited by the expert's knowledge. It is very likely that the expert's knowledge is incomplete. Humans are, of course, not perfect, and it is also not necessarily the case that the expert can perfectly encode it in the form of logic rules. But this is not an issue. because the model can simply learn from data what it needs in addition to the expert knowledge to be accurate. You can even show theoretically that this model is, thanks to the rule generator, as expressive as the most expressive machine learning model, so it can really learn whatever it needs from data in addition to the expert knowledge. We've discussed how concepts form the basis of our model, how logic rules build on concepts and provide us with interpretability, and how the rule generation then really gives us this nice interaction and expressivity. This means that we tick all these boxes that we wanted to have at the beginning, so hopefully we'll be successful in the future when we apply it to this use case of smart grid decision support. And if we are successful with this, then maybe the lights will still go out from time to time in your home, but at least the system can tell you why that still happens. That's at least something.